Welcome back to System Software. All right, so last time we covered arithmetic and branching, how to translate those programs, how to write them in assembly, and how to translate them. And today we're going to start on the content for the last project, CoGen 3, and that's supporting pointer operations. So the actual code for the compiler is pretty short for this, but the getting it right is complicated. So if you've always struggled with pointers, they are complicated, but I think seeing how they work under the hood will actually make it easier to understand them. And so we're going to go through it for the next several lectures slowly and carefully, and hopefully this will help you really understand pointers and why they work the way they do. All right, but before we get into that, questions about the last class, questions about the CoGen projects? Yeah. For the return value? Yeah, that's part of the calling convention. The System 5, that's the Unix calling convention for x86-64. It's just a convention, but that's the convention we use to integrate with the rest of the system. So that's why when you return something from your main method, the loader will actually receive that value. The C runtime of the loader will actually receive that value on Eustace and report that. You know, when you say echo money sign, that gives you the return code, the exit code. And that gets from main to bash because we use REX, because we use the same convention. Okay. Oh, you can't see that screen. Sorry. So that's when you use echo money sign question mark. That's why you can see the value from your return because you're using the same convention that all of the other system software is using. All right, I think was there another question over here? Yeah.
So for CoGen 2, will we replace the R5 functions stored with our code in the handbook?
Yeah, that's right. So you can certainly use yours if you like, but if you're worried about them being correct, then you can use the hard-coded ones that I've given you. And the reason this will work, so this is not the full implementation. This is an implementation that works just for this IR file. So I've compiled this IR file, this simple IR code, into assembly, and then I just hard-coded that assembly code into each of the 5 function listeners, the listeners for the function structure, so that it'll work. Yeah.
In our code, do we have to split del, or can we just put \n at the end of this?
You can put \n, because we're only going to be testing on Unix. I think this is just for systems like Windows where they use carriage return new line /r/n.
I read that it was like, basically what it flushes the buffer.
Okay, so I don't know about C++. In C, when you put a new line character, I think of any kind, to print F or to the C library version of the files, it will flush the buffer, as far as I understand. I don't know about C++.
Yeah, I used to use that when I was first looking at C++, and I just switched to using \n. But for this project, I was using ndel, but I was like, man, I wish I could just use that \n, but I was using ndel just to be safe.
You can use \n. You can use \n. I mean, even if it is flushing the buffer, it doesn't matter. It's all going to be flushed eventually. And we're only running on Unix, the Unix world. So it shouldn't be a problem to use \n. Yeah. Yeah, they'll be the same hard-coded parts. So for CoGen 3, it's just like CoGen 2, where there's statements within the body of the function. So I haven't put up the CoGen 3 exercise yet. I have it here being released next Monday, but I'll put it up earlier than that. You can actually get started on it. It's going to be except for the test cases, it's going to be the identity. I'm just going to copy this project description and just put the listeners for pointers here. So the handbook already tells you. The CoGen handbook already tells you which functions are part of CoGen 3. So if you just follow the same instructions for CoGen 2, use the same hard-coded functions, hard-coded listeners for implementing functions, and then implement these 3. I'm only going to test these 3 and enter a sign. So it's the same as It's the same as this CoGen 2 table where all of these are given to you, except you implement the 3 pointer related operations. And there'll be different test cases. But yeah, I'm literally just gonna cut and paste this document, replace CoGen 2 with CoGen 3, change this table, and change the test cases. And that's all I'm gonna do. All right, other questions on CoGen projects? So I did grade CoGen 1. I had it running when I left yesterday, and I just uploaded the grades today, so you should have your grade. Yeah.
Does Emacs have a feature where you can go to a type and then see where it's defined? Because what I had to do was I pulled up the project in VS Code alongside it in Emacs, and then just to see what the instance variables of each class was. VS Code you just can both on the type and it pulls up where it's defined and intermediate. But I was writing everything in Emacs and I couldn't figure out how to do that in Emacs.
Yeah, Emacs can support that. I think it requires some setup. I haven't done this for a long time. I think Emacs can do that, but I don't think it's out of the box. You have to use some external tool, I think, to do that. So apologies for the if you're used to the kind of automated documentation. I tried to put everything in the handbook that you would need, all of the reference stuff, although it's not in a reference in one place. But yeah, if you use VS Code for reference, that's totally fine. Even if you don't want to use Emacs, that's fine too. It's just kind of, if you use that with Eustace, it adds a whole bunch of bloat to Eustace. Yeah.
I tried it once for the debugger and it destroyed my storage, so I just learned how to use GDB.
Oh yeah, good. Yeah, use GDB. Yeah, it's the same thing. Well, it's just GDB is a little more archaic to use.
I had to change the make file to include debugging permissions.
Oh right, yeah. Maybe I should do that.
You just add -G to the
Yeah, -G. Yeah, we'll do it. Had some. I tried to link to stuff here for doing that, but yeah. So I tried to put everything in here, but let me know if something's missing. I tried to put all of the member fields, but it's not as a reference. It's in prose. All right, so yeah, CoGen 1 grade should be up. I wanted to get these up so you come to office hours if you have any issues with those. Looks like people did pretty well. It looks like half the class got all the test cases passing. And several people, I think, just are waiting, are not, using the resubmission policy to wait. So, all right. Any other questions on anything through the class? Logistics, content, stuff from last time. All right. Let's do homework. So homework 23. So this was about using assembly branch instructions. So I worded this by saying assembly code that has equivalent branching behavior. Just to say that it doesn't really matter whether you follow the calling convention or whether you use memory or the stack. You could do anything you want with the other instructions. That's why I said it like that. If you did it, a whole exercise with simple IR and the calling convention, that's great. That's good practice for the CoGen. But it was really just to test the branching behavior. So for this, for labels, what do labels look like translated from simple IR to assembly? They're identical. They're basically identical. So this head label just looks like the same thing, the head label. What about simple IR go-tos, conditional go-tos? What do they look like in assembly, in AMD 64 assembly? How do we implement this conditional branch in Intel assembly? What are the instructions that you can use for this? Yeah. Yeah, you do compare, and what's the order of the operands for compare? The left operand is the second operand, so if I set, so if A is 5, one way I could implement this is to move A's value into RAX, so that implements this, and then use A's value as the second operand for compare. And the right operand of the less than or equal to is 0, so I could put that into RBX. And this would be the comparison. And then once you have done the comparison, how do you branch? What's that? JLE, yeah. So there's a different branch instruction for each condition that you'd like to test against. So JLE is J less than or equal to, JL is less than, JG is greater than, JGE is greater than or equal to, equals, and not equals. So that table is in the class notes from last time. So jump less than or equal to, and then you just put the label, A1. That label will be down here somewhere. What about a conditional, unconditional branch? Well, it's just a jump. Jump to head. So as long as you have this is all I was looking for in this homework. The rest of it is an exercise in arithmetic and variable assignment. Any other questions on this homework? Okay, let's take attendance. Today we're going to talk about pointers. Pointers in simple IR, which are very much like C pointers, and how to translate them to what they look like in assembly, and also how to translate them. So we'll be doing this over the next 3 lectures. So let's first review the semantics, the behavior of pointers in simple IR. So remember, in simple IR, everything is a 64-bit integer. There's no other types besides that. They're all integers. We've got 3 pointer operations. We have reference. This takes the address of x, not its value. Takes its address and stores its into T1. So T1's value is now the address of x, not the value of x. Questions on that? Has anyone not seen this in C or other languages? Who's seen it? You've all seen it, right? Seen reference. Okay. It's covered in like CS1, CS2, CS1, okay. Then we have dereference, which takes the value of T1, takes T1's value. So in this previous one, T1's value was set to the address. We take T1's value and treat it as an address. We look up the value that's in the address given by T1. That's why T1's a pointer. And we take that value, not the value of T1, but we take the value at the address that T1 holds and store that into T1. Into T2. Store that into T2. So we take T1's value, look that up in memory, get the address at that location in memory, take that value and store it into T2. Questions about dereference? I think everyone's seen dereference. I think you would had to have for implementing algorithms in CS1. All right, then we have dereference assignment. And in simple IR, I make this a different instruction. And that's because the assembly for this actually is different. The dereference behavior here is a little bit different than the dereference behavior here, as we'll see when we get to this. So this is a completely different construct in simple IR, and it takes the value on the right-hand side, whether it comes from a constant or from a variable, and it doesn't store it into the address of T1. It doesn't associate it with T1 itself. It does a lookup to T1, takes that value, treats it as an address, goes to that address, and then stores 11 in that address. So that's why T1 is a pointer. Questions on this? Questions on this behavior? So let me do each of these diagrammatically as well. So if T1 and X are some memory locations, then when I take the reference of X, T1, you can think of T1 diagrammatically as pointing to the value of X, pointing to X's memory location. So this is diagrammatically what T1's pointer behavior looks like. For T2 equals the dereference of T1, if I've got T1, X, and T2, if T1 is pointing to X's value, if I take, so let's say X, oops, let's say X is 9 at this point, and I set T2 to be the dereference of T1, what's T2's value going to be? So T2 does not equal T1's value. The dereference pointer, the dereference star means follow the pointer to the value of X, or the value of this memory location, and assign that to T2. Yeah, question? Oh, okay. Questions on that behavior? All right, then finally we have the dereference assignment. So we have star T1 equals 11. So if we have our same setup where T1 is pointing to X, T1 is pointing to X, then what's the result going to be for T1 and X after this dereference assignment? So we take 11 and we assign it to whatever address T1 is pointing to. So go ahead. Yeah, go ahead. Yeah, X will be 11. That's because we don't assign to T1. We take whatever the address T1 is pointing to and assign 11 to that address. So X, what X is currently associated with in memory, will be set to 11. Questions on this? Question on this behavior? So hopefully this is review of CS1. Okay, so let's take a complete example, go over a complete example, just so we're all clear on how pointers operate. So firstly, take a look at this program for a second yourself and work out in your head what value gets returned by this program. And I'll start diagramming this. All right, what value gets returned by this program? 11. So people are saying 11. Okay, so let's see why that is. All right, we have the first assignment here, X equals 8. So the memory location associated with X gets set to 8. Questions on that? All right, same with Y. Y's memory location gets set to 9. That's this instruction here. And then here we have our first reference. So we take the reference of X and assign T1 to the reference of X. So this is diagrammatically like setting a pointer to X. This is how you probably learned it in CS1, using arrows and boxes to represent pointers. Okay, then we have T2 equaling the dereference of T1. So what's the value of T2 going to be at this point in the program? It's going to be 8. Yeah, right, 8. because we don't assign it to T1's value, we assign it to the dereference of T1's value. That is, we assign it to the value of the variable that T1 points to. So T1 points to X, so T2 becomes 8. Now the next instruction is a dereference assignment. How is this state going to change after this dereference assignment? Yeah. X is going to be 11. So this takes whatever the value of T1 is. T1 is a pointer. So we dereference the pointer, following the arrow, following the address. That points to X, so when we assign the dereference of T1 to 11, that actually updates X. It doesn't change T1. And then finally we have T3 being assigned to X. And so how does the state change? Well, there's a regular assignment. So it copies whatever the value of X is into the memory location for T3, making T3 11. And finally, when we return the value of X, which is 11. So questions on this example? Questions on the pointer behavior? Was this easy to follow or hard to follow? Hard to follow? So pointers, I think pointers are one of the more confusing parts of learning about C. And hopefully, stepping through it in a diagram, I think hopefully helps. Okay, so that's the semantics, that's the behavior of pointer operations in IR. So to see how we implement this in assembly, let's first go back and look at how variables are allocated at runtime. And so where are variables stored in our simple IR functions? How are variables stored? Offsets from RBP, right? What is RBP pointing to? It points to the base pointer. What's the base pointer for? What's that? Where is the base pointer pointing? Is it pointing to the heap? Is it pointing to the code segment? Pointing to the stack, right? So each function gets its own stack frame. So these local variables, they're allocated at runtime in the stack frame. So that's what we learned about when we learned about functions, implementing functions in assembly, and the calling conventions. So let's take this same example and let's show how the stack gets changed when we run this program. So let's take this main function and let's draw a stack frame for it. Just as a quick review, what's in the stack frame for main here? What's the first thing in the highest address of the stack frame for main? What do we have? What about parameters? Are parameters in this stack frame? Some of them might be. What about for this example? So what about this example in our System 5 ABI? Those are in registers, right? So if there were more than 6, we would have parameters, and those are considered part of main's stack frame, those parameters. But okay, so the first thing that's going to be here is a return address, and then what's the next thing on the stack? Yeah, the old base pointer. The old base pointer. And then what do we have, depending on how closely you're looking at my implementation of the compiler? Yeah, and you have the local variables. In the code I gave you, I also push RBX to save it, but let's ignore that. RBX it's just a register, but if you use it in your function, you have to save it. So the calling function expects RBX to not be changed. So it's just part of the calling convention, and it differs per machine. Yeah, if you don't use it, you don't have to save it. Yeah, exactly. So I probably unwisely, I should have used a different register. I used it because A and B are nice parameters parameters to use. Otherwise, it would be like RAX and R10, which I actually might switch to next time. But all right, so let's just forget about call save registers, and let's just put all of the local variables here. So we've got A, B, X, y, t1, and t2. Let's give all of these concrete addresses. So let's count up. So let's say this is 64, 72, 80, 88, 96, 104, 112, 120. Did I get this right? Okay, so when we enter this function, after the prolog is set up and the stack frame is all set up, what's the value of RBP? You can say it out loud. 112, yeah. So RBP is here. RBP is 112 at this point. Okay, good. So this is our setup stack frame when we've finished running the prologue and we're just about to run the first line of this program. Yeah.
Is there any reason why we need to put T3 down as well?
Oh, because I forgot it. Sorry. Thanks. Fortunately, I didn't start at 0. Sorry. Yeah. Thanks. We're going to need that for this. Yeah. Thank you. Okay. And then, how at runtime do we access these variables? Offsets from RBP, right? So let me put the offsets here as well. So this is, let me move this over a little bit. So this is -8 from RBP, -16 from RBP, -24 from RBP, -32, -40, -48, and -56. So this is the offset, and this is the name. So this is exactly what your symbol table looks like in your compiler when it's running. Or this is the structure of the symbol table. It may not be, with RBX it may be off by 8. But. Okay, so let's run this same program, but use the actual addresses we have here. Okay, so when we assign x to 8, what is the code generated by enter assign, how does it change the state of this machine after the instruction is completely executed? So what memory address gets updated here, and how does it get updated? Yeah. Yeah, so 8 is stored in the location associated with x. The location associated with x is RBP -24, which is 88. Okay, what about y equals 9? Same thing. So the memory address for y gets 9 stored into the memory address associated with y. Okay, so now what happens here? What happens when we get a pointer to x? How does the memory locations, or how does the value of the state of memory change here? So T1 is being assigned to be a pointer to x. So what value gets stored here, right? We can't draw an arrow. There's no notion of an arrow in x86, 64. So yeah, go ahead. It stores 88. It stores the address of x. That's what this operation does. So conceptually it makes a pointer, but physically what it really does is it takes the address of x. And so the address of x is RBP -24, whatever RBP is. But in this execution of the program, the address of x is 88. So what literally gets stored in T1 is the address 88. Who has not seen this before? Okay, this was covered, right? This was covered in like CS1, that it's literally the address in memory being stored here. Okay, good. All right, so that's how the state of the machine changes when we have this operation, the reference operation. Literally takes the address of x and stores it in the address associated with T1, which is here, address 72. Okay, so let's do the next instruction. T1 equals the dereference. T2 equals the dereference of T1. So knowing that T1 is a pointer to x, what value will T2 have after this instruction? It'll have 8. Good, yeah, it'll have 8. And that's because what it does is it takes T1, which has this address, and it follows the pointer. It dereferences the pointer to address 88 and takes that value and puts it in T2. Questions? Questions on that? All right, now we've got this dereference assignment where we assign the dereference of T1 to be 11. So how does the state change after this instruction is complete? Yeah, exactly. Address 88 now has value 11. And that's because we took T1 again, which has value 88. That's the literal binary integer value it has stored in memory. We take that value and we go to the address and do a store at the address held in T1. So we take 11 and store it into address 88. Questions on that? Questions on that one? That's maybe the trickiest one to think about. So star T1 takes the value, so it takes T1 first, which is 88, and star means go to that address, address 88, store the value on the right-hand side in that address. All right, and finally we have just an assignment, a variable assignment, which its semantics says copy the value of x into T3. So it's going to take 11 and copy it to T3. So no more pointer operations here, no more references, just a copy between memory locations. All right, questions on this? Yeah. Wait, say again? How come, say again?
How can the computer tell if 88 is not an actual value?
It's a good question. The computer cannot tell. The computer does not know. It simply trusts you, the programmer, to use the right instructions. So if you were to make a mistake and instead, like say you had the wrong offset for T1 and you used 9 instead of 88, and you told it to store in address 9, then the machine would do exactly what you asked it to do. It would try to store in address 9. And if your process has access to address 9, it's going to overwrite it. So if there's no protection, say, on your code, if your code is in address 9 and you overwrite it with the value 11, once it gets to that code location, the processor is actually going to try to run whatever opcode may be encoded by 9. Does that make sense? Yeah.
I was coding something in C++, like I was trying to shuffle an array that was just filled with zeros and ones, and then for some reason afterwards there was like a 10 in there, and I was like, how did that even happen?
Yeah.
I went out of bounds in there, and it like shuffled it alongside some unrelated variable that was holding a 10.
That's right. Yeah. I mean, like at the machine level, it's all just one giant span. It's basically a giant array. And all this stuff is like kind of a virtual layer on top of it. And because, C and C++ allow undefined behavior, like out of bounds, or at least most compilers will not stop you. It will just translate it to the easiest thing it can, which is to just go out of bounds, reference stuff out of bounds. This is also where Stack Overflow attacks come from, which I think I mentioned before. Because arrays have positive increments, if, say, A is an array, and offset 0 is this value, offset 1 is here, offset 2 is here, that means the return address, if A was not supposed to be an array, or B was not supposed to be an array, but I access it out of bounds, I can actually overwrite the return address and cause your program to return to the wrong address, return to a different address. And very clever attackers can make it return to their code. So they're running arbitrary code as your process. All right, questions? Other questions about this layout? So, the thing to kind of keep in mind here, as the two questioners pointed out, or two comments pointed out, is that the machine does not know whether these values are addresses or integers. This is, maybe I talked at the beginning, these methods of abstraction in programming languages. It's the use of the value that defines what it is. So at the machine level, these are just binary encoded values. They're not even values. They're just like electrical signals, high voltage or low voltage. we say they represent 0 and 1, but physically they're just different voltages. And you can apply whatever machine operation you want on these combinations of voltages. If you apply one that does a memory lookup, it doesn't care whether you thought that this was an integer or a floating point or a string or a character or an actual address. It doesn't care. It's just going to take whatever value you give it, whatever sequence of binary digits you gave it, and it's going to treat it as an address, no matter what you thought the value was. So this is what type systems is. What programming language abstractions do is they provide meaning to these values, but at the machine level, they don't really have meaning independent of how they're used. So in the same way that a baseball bat may be a really fun game, or it might be a really bad weapon. The baseball bat doesn't really care whether you think it's a weapon or a toy. You know what I mean? So this is well. Anyway, in philosophy, this is called teleology, where you believe the purpose of an implement is somehow intrinsic to it. But in computer science and science in general, the machine, the object, does not care what you believe its purpose is. So same thing here. This is just sequences of bits. All right, other questions on this example? Okay, so let's, so that was the, so this is the behavior of pointers. So hopefully this makes it a little clearer how pointers work. So if you've ever been confused about pointers, or you ever are confused about pointers behavior in a program, you can always just write it out literally how the machine uses it. Make up an address for it or draw a box to point to something. But if you make up an address, you can see more physically what the machine is actually doing and see what that algorithm is doing when it's using pointers. If you just remember that, well, it's just an address here, and dereference is just taking that value and doing a memory operation on that value. Okay, so let's see how we can actually implement this in assembly. So first, let's refresh how we do assignment. So if we have a local variable, like let's say we have x, how can we store a value in x? So let's say we already have let's say we want to store 8. We want to do this assignment. What does the assembly look like for that assignment? Yeah.
Would it be mod and hash symbol 8 and minus 24 RBT?
Good. Yeah, exactly. So it'd be mov, which is move. It's short for move. But yeah, mov, money sign 8. And then, the offset from RBP, and how we do that in AT&T syntax is we put the offset first. So it has -24. This is the offset our compiler had assigned it. And we use this syntax here to say, give us an offset from RBP and store that value 8 into this address. And so if you notice here, this actually looks very much like a dereference. This actually is a dereference. This is dereferencing. This is a dereference assignment, right? Because it's taking the address that's stored in RBP. Because remember here, RBP literally holds an address. It holds this address value. Its value is 112, which if you treat it as an address here, then the consequence of this instruction would be to take this value 8 and store it here in memory. So questions on this? Questions on how assignment works from a couple weeks ago? Okay, and we're going to start to see, how we can actually start using this same kind of assembly syntax to implement pointers. Okay, and so what makes this ultra confusing is that the assembly instructions for dealing with local variables is actually using pointers, is actually using references. So what's going to be very confusing here is that we're going to have multiple reference operations happening to implement the same pointer instruction. But all right, so let me just start to get into the example. So let's take this instruction. So this is T1 equals reference of X. So remember, this was the instruction here that took the reference of X, so X is at address 88, and stored it in T1. That's the instruction that we're going to write assembly for. Okay, so how can we, so knowing that RAX is here and knowing that it's RBP, it's an offset from RBP, let's try to think, like, what assembly instructions, given the small number of instructions that we have, what could we use to compute this value 88 so that we can store it into T1? Yeah.
I think it would be like the same principle that we did for moving 8 into the other variable, but instead of 8, we would just put the address according to whatever T1 would be, according to whatever X would be. So I'm not sure, I don't remember the X or X.
Well, so remember, we're not taking the value of X.
But the address.
We're taking the address of X. So how can we, so in this diagram at runtime, we can inspect memory and say, well, it's address 88. But how can we, in our compiler, generate code that will give us that value? Yeah, go ahead.
Store T1. You know how we put a parentheses for RBP that we put another parentheses to get the number address location that also.
We're getting there. So that'll be for if we want to store into a pointer. So we're getting there. So we want the address somehow. We're going to move it. We want to somehow use that syntax. So yeah. What? Okay. So now we're all taking all these pieces together. So what we can do is we can generate code that will compute the address for us at runtime. So at compile time, all we know is the offset, and we know that RBP contains the address of the stack frame. This is what we know. We know that RBP will contain the address, and we know that RBP minus 24 is going to be the address of X. So what we can do is we can generate code that will compute that for us at runtime. So here's what this looks like. So actually I have the here. So what we're going to do is we're going to start with the value of RBP, the value. We're actually going to copy it, and we're going to add the offset or subtract. The offset is negative, so if we add a negative, it's subtraction. We're going to subtract the offset and then store that result. So we're first going to generate code that will compute the address. So this is that where you have to kind of wrap your mind around the runtime versus compile time. Compile time, we don't know this information, so we generate code that will have the information at runtime. This is the kind of essence of compilation. Okay, so what does this code look like? I have myself. I have a lot of steps. I have a lot of build up here, but I have it in my slides. So, okay, and as we saw here, if we have RBP already and we subtract 24 from it, we're going to get 88, and that's because these are our offsets. All right, so this is what the assembly code will look like. We first take the value of RBP. Remember, the value of RBP, its contents here is 112. So at this point, this instruction doesn't know or care that it's an address. It's just taking whatever its value is and storing it into RAX. With me so far? And now we subtract or add a negative offset. We add negative 24 to RAX. So in this diagram, what's the value of RAX going to be at this instruction? 88, right? Because we stored 112 into RAX, and then we added negative 24 to whatever RAX was. That will give us 88. Now, at runtime, we can inspect memory and see that this is 88. At compile time, we only know RBP, so we generate code that will have a guarantee that RAX will hold the address of X. The register will hold the address of X. Questions on this? Does this kind of make sense? So this is the assembly version of just saying. This is the assembly version of just saying RAX equals RBP minus 24. So we're going to write out this code. We're going to generate this code. 'Cause remember, we're not computing the value at compile time. We're just generating code. And we're going to generate code that will compute the value that we want it to have at runtime. So this assembly code is equivalent to doing this. Okay, and then finally, how do we store into T1? So remember, we're just assigning whatever this address is to T1. How do we do a store into T1? So forgetting about any pointers or anything like this, how do we just store a value into? Yeah, exactly. So finally, to store the result into T1, we just move whatever RAX is. This instruction doesn't care what RAX is, doesn't care that it's an address. It just takes whatever that value is and stores it into the memory location for T1.
So that the cache symbol, like whenever we're doing the move, doesn't that not like automatically like make whatever's next to it an integer? So, like,
The money sign? Yeah, this is an immediate value. Yeah.
Could we like, well, I don't know if it's even possible, but couldn't we just like store an offset like next to that, like according to whatever we're trying to like put the address from? It's kind of like crazy to think about, but like, can you just put the address of whatever you're trying to get there next to that cache symbol and it would make it an integer?
Well, you could. The problem is we don't know at runtime what the value is. So because the functions may be called in different orders, we can't necessarily predict that order. The operating system may load stuff into memory in different locations. And so the address of the actual stack frame, the address of RBP, may not be something we know at compile time. So if we knew that at compile time, sure, we could just take that address. So if we did static allocation of everything, we just predefined the locations of everything, yes, we could. That's how we could do the pointer. But because we allow sort of arbitrary function calls, and our compiler doesn't want to have to compute those values, and the operating system may actually, in fact, move addresses around in memory for security purposes, instead we generate code that will compute the value at runtime.
So rather than like trying to do like about it in every possible way for every specific way, you just get a general template on how to do it.
Yeah, you kind of generate code that will do it. So imagine you have a recursive function where the stack is growing after each recursive call. This pointer address is going to change after every call. So we won't know at runtime or at compile time what the absolute address of every function local variable will be. But we don't know the value of RBP, but we know the invariant that RBP will always hold a pointer to the stack frame. And we always know the offset of each variable from the stack frame because we as the compiler writers generate code that ensures that that will happen. So you can call this, maybe if you take discrete or whatever, this is called an invariant. So something that will always be true for the lifetime of the program. So something that will always be true, except during the construction of the prologue, is that RBP will always point to the stack frame. Unless you have some security exploit which violates that invariant, but the compiler writers write code assuming that that's the case, assuming that there will be no undefined behavior. Make sense? Other questions on this? Yeah. To RBP?
No, not the RBP, just to like...
To here?
Yeah.
Yeah, you mean like you first move RBP into T1 and then subtract, for sure. Yeah. There's a lot of ways to implement it. There's many ways to implement it.
But you're not forced to. So add isn't an instruction where you're only allowed to search strings.
No, you can use it, but only one can be a store or a load.
Okay, so you can't like add between two.
Right? Yeah. You can't in the Intel architecture. Yeah, they'll only do one load or store per instruction. And I think in MIPS maybe doesn't even allow a move with a add, or does it?
Yeah.
I'm not sure.
Yeah, MIPS add all of the only instructions that let you load and stores are explicit load and store. So anything else it has to be registered.
Yeah, it's like the classic RISC. So, Intel has these, really under the hood, there's like a whole bunch of different add instructions. There's like an add instruction for each like combination of arguments, basically. But the mnemonic is the same, and then the assembler sort of figures out. It's like almost its own little programming language. But yeah, so you can only do one load or store for these move and add instructions. Like you can't even move between two memory locations. You'd have to do, to an intermediate register first. But yeah, this is the way I did it in the compiler. I used add because the symbol table has the negative offsets, so I don't want to have to convert it. So if I do add, then it'll always work. All right, questions on this? Other questions on this? So let's take a look at what this looks like in this diagram here. So I kind of skipped ahead a bit. I don't want to overwrite this because it's kind of a nice, it shows the final answer. But remember, this is the code for storing the reference of X. Where can I put this? So this was T1 equals reference of X. And this is the assembly code for it. So what this looks like, it's the same behavior in our machine, except now we have the actual machine instructions for this. So what will happen is the first instruction will set RAX to be whatever RBP is. RBP is what? RBP is 112. So move RBP to RAX. We'll set RAX to 112. And then we add negative 24 to RAX. So that will set RAX to be 88. And then finally we have move RAX into the memory location given by RBP minus 40. So this is RBP, which is 112, minus 40, which is T1. And so this move instruction will take whatever RAX is, which is now 88, and move it into T1's address. So that's why 88 gets updated here. And so actually this kind of memory indirect offset addressing mode or whatever, this is doing the same computation that we're explicitly doing here. Under the hood, this is what the processor is doing. But this gives us the memory location. It doesn't give us the value of the memory location, the actual address. All right, questions on this? Does this start revealing how pointers work a little bit more, maybe under the hood? Hopefully making pointers not so scary. Although maybe it makes assembly scary. All right, any other questions on this? Everybody pretty clear on this code? Okay, so how might we generate this code with CodeGen? So we see this operation. What might we do to generate the assembly code? What parts change? So if this is we take this as kind of a template, what parts are going to be the same and what parts are going to change depending on the input instruction? So let's say this was T2 equals address of Y. What's going to change here? Offset's going to change. So what's the offset going to be for Y? It's going to be negative 32. And what's the offset for T2 going to be? It's going to be negative 48. Is anything else going to change? No, right? So we have this. We can kind of back out or abstract away a template for this. We could say, all right, this is whatever the offset is, the offset of the right-hand side, and this is whatever the offset of the left-hand side is. And so when you write your compiler, all you really need to do is spit out this code, but replace these offsets with the corresponding symbol table offsets for the right and left-hand sides. Okay. All right, let's take a look at, so any other questions on this? Any other questions on referencing a pointer? All right, let's take a look at dereferencing now. So remember that we're taking T1 as a pointer to somewhere in memory, and then we're getting the value of that memory, value that's being pointed to by T1, and setting it to T2. Okay, so similarly to before, we're getting the address and storing it somewhere. What assembly instructions load a value from a memory address? In the Intel, the x86 or Intel AMD 64 AT&T syntax. How do we load it? Well, it's the same as what we saw with RBP when we wanted to load. For instance, here when we wanted to store RAX into a memory address for a variable, we can just swap that. We can when we want to store it, we can load from the address of T1, so the address of T1, we can load that into RAX. But this syntax, if you take away the offset and just use parentheses like here, this will basically do a pointer dereference. So that's why the offsets from RBP work, because what this says to do is to take the address of RBP, subtract 40, and get that value, either load or store that value. If we don't do the subtract 40, it's just going to load or store whatever value, whatever address is given by the value of that register. So here, whatever value is in the register RAX, that's the address we're going to use for our store. Sorry, for our load. So RAX, whatever value it is, this is going to treat it as an address, and it's going to do a memory load from that address. Okay, so when we do our dereference lookup, we need to first get the address that we want to load from. So that's given by T1, and then just load from that address. So we get the value of the deref variable, so that's going to be the address, so it's the value of the variable. And then we get the value of the memory at that address and store it into our variable. Okay, so let me diagram this first. So our memory load. All right, this is our Actually, I can just have this here. So this is our instruction. So what did we do? We took whatever the value of T1 was, which is 88, and we did a lookup at address 88, and then stored that value 11 into T2. So the first thing we need to do is we need to get the address given by T1. So how do we load this value into a register? So how can we take whatever T1's value is, how do we load that value and store it into some register? Well, it's the same thing we saw here. We take the value of T1 and put it into a register. Make sense? So that's the same thing we did when we did an assignment. And then we need to not take this value and store it into T2 or whatever. I keep forgetting what the value, which one it was. That's not So it's T2, yeah, it was T2. So we don't want to store this value into T2. We want to store the value given by the address that T2 has. So to do that, we use this indirect addressing to take whatever address is in RAX and do a lookup to that address and store that into RBX. And then finally, we can store that value into the address associated with T2. So without this middle instruction, this first instruction and this last instruction are almost identical to an assignment. So if we were assigning T1 to T2, we would just take T1's value and copy it to T2. But instead, we take T1's value and then load the value at that address into RBX, and then move that value into T2. So let me show you what that looks like in our diagram. And I think, yeah, this should be fine to do it like this. Let me give myself some space here. All right, so after the first instruction here, we take the value of T1, which is 88, and we store it into RAX. So right now, it's in RAX already, so it's just going to be overwritten. And then we load the value given by RAX into RBX. So we're not taking RAX and copying it to the RBX. We're taking 88 and doing a load from address 88 and storing it into RBX. So right now, that value is 11, although I think in the original program the value was 8, but here the value is 11, and store that into RBX. Questions on that? Questions on the second instruction? There's a key difference between assignment and dereference, or dereference. So we take whatever the value of RAX is and do a lookup into memory, get that value, and store it into the register RBX, the destination register. And then finally, we store whatever RBX is into T2, the address given by T2, which is negative 48 offset from RBP. Questions on that? Questions on those steps? Okay. Okay, so let's see again how we can compile this program in our compiler. So what changes or what differs between different dereference assignments here? So let's say we had x equals dereference of y. So how would this program change if we had x equals dereference of y? So what would be this offset instead? Would it be x's offset or y's offset? This is y's offset, right? This is y's offset because we're taking whatever value y has, which we can get from offset 32 from RBP, storing into RAX. And then does this code need to change? No change, right? Because we now know that RAX will have the value of y. And we go to whatever address y has as its value. So it might not be an address you can access, you might get a segfault, but the machine instruction will take whatever RAX is, treat it as an address, do a load from that address, and store the value into RBX. So whatever RBX, whatever value address 9 had, that's going to be an RBX. And then when we move RBX into the address associated with X, so how will this offset change? What will this offset be instead? It'll be 24, the offset of X. So the code template for for this instruction is the offset of the right-hand side and the offset of the left-hand side. So if you just look at like the code, it doesn't look that different. I mean, it's like if you were just to stare at it and you didn't know what you're looking at, it would be like very minor distinctions between all of these. But if you understand the operation of the machine, understand how pointers are operating and how you use assembly to do it, then the sequence of instructions is actually pretty simple, or at least there's a few number of them. But the behavior of it and how the machine changes, that's the complicated part. And making sure you correctly generate this with the simple IR input, that's going to be the hard part. All right, questions? Questions on either of these pointer operations? Okay, so let's save the last operation for next time, and there's a homework up for this. So it's just going to be testing out some of the assembly code that we did today. So if the variable x has an offset -24 for the base pointer, write assembly code that will result in the address of x being stored in RAX. So hopefully that sounds familiar. We covered it in class. And let's leave it at that. So pointer's a little bit of a brain teaser, so can end a little early. All right, everyone. Have a good one. Have a good week.